Alright folks, hello and welcome to this video lesson on section 5.7, apply the fundamental theorem of algebra. And as always, I suggest you take notes in your notebook, write down examples, pause the video as needed to make sure you get down all the information. So first I want to restate the fundamental theorem of algebra, which is actually stated in your book as a corollary, but it's okay, we're going to just consider the corollary the fundamental theorem for our purposes here. A corollary is something that follows directly from a theorem. So here this stands for fundamental theorem of algebra, and it tells us that if f of x is a polynomial with degree n, then the equation f of x equals 0 has exactly n roots in the complex numbers. And then in class we added that additional note that a double root counts as 2 roots, and a triple root counts as 3 roots, etc. So just remember that when you're writing out the fundamental theorem. So what does this tell us in practice? Well, this says if we have a function, theoretically, any function, f of x equals, 2x cubed minus 4x plus 1, the degree is 3. So we know that degree is 3 because the highest exponent of a variable there is 3. So what the fundamental theorem of algebra tells us is that the equation, if we were to rewrite this as an equation, let's say 0 equals 2x cubed minus 4x plus 1. If we were to solve this using, we try the rational root theorem, we might try, after we get it down to a quadratic, we might use the quadratic formula, etc., etc. When this is solved, it's going to exactly have n roots in the complex numbers, or it must have 3 roots. There's no promise that these roots are going to be real numbers or that they're going to be rational numbers. There could be square roots involved, they could be irrational, but we know, based on this fundamental theorem, that there has to be 3. So theoretically, if there's 3 roots, this can be written as x minus the first root, x minus the third root. I'm sorry, why would you go from 1 to 3? That doesn't make much sense there. The second root, and x minus the third root. And this would be quote-unquote factored, but the reason I put quotes around it is because technically we reserve that word factoring in Algebra 2 for writing with factoring over the integers. And this would be quote-unquote factored over the complex numbers, or there could be radicals or imaginary numbers involved. But either way, what you need to know is that it is possible. If you find out what the R1 and the R2 and the R3 are, you can write this equation or this polynomial using this method, x minus R1, x minus R2, x minus R3, and we know that because we know that there's 3 x's that we can plug in here, or an x we could plug in here to set it to 0, we could plug something in here to set it to 0, and plug something in here to set it to 0. Now where does the double root come into play as well? Technically, 2 of these could be the same. Right, the R1 might be the same as the R2, and then that would be considered a double root because there would only be one distinct root, but it's listed twice in our quote-unquote factored expression. And what about a triple root? Well, technically R1 could equal R2, which could equal R3, and then we'd have what's known as a triple root. So that's a little way of thinking about the fundamental theorem, and just keep in mind that any polynomial can be written like this based on its degree. We have a couple more theorems that are going to help us analyze the types of roots that equations will have or zeros that functions will have. And the first, and these both deal with conjugates. So you can pause the video and make sure you write these down. But the first is the complex conjugates theorem, which basically says if a polynomial function has a plus bi as a 0, then it will have a minus bi as a 0. So if you have one of those imaginary numbers, that complex number with an imaginary part, you must have the conjugate. If one's a 0, then the other will have to be a 0. Also some restrictions, just so you know, a and b have to belong to the real numbers here with this theorem. Okay, so for the second theorem we have irrational conjugates, meaning if you have a polynomial function that has a plus square root of b as an irrational 0, then a minus square root of b is an irrational 0. In this case, A and B, or rather, sorry, A will have to be a rational number. It'll have to belong to the rationals. And the square root of B will be irrational. Is irrational. Okay, so this would count for something like the square root of 3, if you had that as a root, because it can be written as 0 plus the square root of 3, and then 0 minus the square root of 3 would also have to be a root. If you came up with 1 plus the square root of 2 as a root, then 1 minus the square root of 2 would also have to be a root. Be careful, technically it doesn't work for this. If 2 square root of 3 is a root, well, we don't have a guarantee that minus 2 square root of 3 is a root, because the form of the theorem does not indicate a coefficient other than 1. So just watch out for that there. And those are two theorems that are going to help us apply the fundamental theorem of algebra. Now let's get to some examples. In this first example, we're asked to kind of work backwards, and they want us to write a polynomial function of degree 3 that has zeros 2, 1, and negative 1. So in previous cases, they gave you a function and they said solve it. This time they're saying, hey, you write the function. All right, Phil is not screaming, you are going to subtract this time. This time he's saying, write the function. Okay, so we are going to come up with a function that we can write using degree 3 and having those zeros. Because it has degree 3, that means it's going to have exactly 3 zeros, and hey, they gave us 3 zeros right here. So if you'll remember from our fundamental theorem, any function with degree 3 can be rewritten as x minus r1, x minus r2, x minus r3. And sometimes the tricky part is figuring out what those different r's are. But that's not tricky in this case because they told us. So I can simply rewrite this as f of x equals x minus r1, let's call that 2, x minus r2, let's call that 1, and x minus r3, well, that's negative 1. All right, where am I getting those numbers from? Well, I'm getting them right here from the roots that they told us, or the zeros that they told us, rather. You have zeros of a function, roots go with the equation. Okay, so this would be an okay final answer. However, it's more polite to write it in standard form, and that will be required when it comes to quizzes and tests and such. I will often ask for standard form, which just means you're going to have to do the multiplication and rewrite this as a polynomial in standard form. So I will do the multiplication quickly, and you can see if you agree with my answer. So actually, why don't you pause the video, try it yourself, and then you can resume the video to check. So there's my work, and there's the final answer for the polynomial function that fits the criteria specified in the example. Let's do one more example. In this case, they wanted to write a polynomial function of degree 4 that has one real zero, negative 2, and a complex zero, 2 plus I. I. Okay, again, we have Phil screaming at us. We don't need to factor or do anything fancy. Oh, he appears he has some chin hair there or some sideburns. And now he is saying, write this function. Well, first let's see if we have enough info to get started. It's a polynomial function of degree 4, which means that according to the fundamental theorem of algebra, it can be rewritten as x minus r1, x minus r2, x minus r3. What the heck kind of a 3 is that? Sorry about that. I am losing it here. Let's get back on track. X minus r3, x minus r4, and it could theoretically be written like that. However, we are given some information about these roots. These roots are not guaranteed to be real or rational or anything like that, except for what they tell us. And they told us that we do have a real zero, one real zero in fact, negative 2. And it also said that we have a complex zero, 2 plus I. Well, based on the conjugate root theorem, if 2 plus I is a root, then 2 minus I is a root. Okay, we are also told that negative 2 is a real zero. And we're also told that it only has one real zero, which kind of might put us in a little predicament here. All right, it appears that we only have one real zero, that's one root, and then we have these two imaginary roots. So what's that third zero? Is it real? Is it imaginary? Or sorry, the fourth zero. Is it going to be real or imaginary? You might say, oh, well, it has to be imaginary because there's no other roots. But that puts us in a predicament because we say, I don't know, it's the imaginary number negative 3i. Well, if that is indeed the zero, well, according to the conjugate theorem, then negative 3 positive 3i would have to be a 0. So in other words, we can't have another imaginary root because that would violate the conjugate root theorem. It'd give us too many roots or too many zeros. But we can't have a real 0 because they told us -2 is the only one. Do you know how to get out of this conundrum? If so, that's excellent. But what we have here is the indisputable fact that -2 must be a double root. Therefore, that will give us the degree of 4 that we want, and it will satisfy the other conditions. So now it's just a matter of writing everything down and getting this polynomial function in standard form. First, we know -2 is a double root, so x minus 2 squared will take care of 2 of the roots. Writing the next part is a little bit tedious, but we have to do x minus the imaginary root. I will use brackets, 2 plus I, and x minus the other imaginary root. I will use brackets, 2 minus I. Okay, I'm following along with our form. Oh my. Don't want to cancel the project, sorry. Press the wrong button there. And that is the form of the equation, and it's now about simplifying, multiplying, and solving. This takes quite a bit of work. It is excellent practice for your algebra. The x minus 2 squared will become x squared minus 4x plus 4. And these will also be trinomials. This is x minus 2 minus I. And this is x minus 2 plus I. So you have to multiply all of these to get your final answer. That's going to take some scratch work, and I suggest pausing the video and resuming after you've done some of the work. Just give a little piece of advice. I'm going to multiply these two first, okay, to get rid of those I components. If you multiply the ones with the i's should cancel out. So I would do that first, and then you can worry about multiplying the reals. So go ahead, try it, and then you can resume the video when you're ready to check. I'm just moving it up here to give more space, but go ahead, try it yourself. Okay, so there's all my simplifying, and that's the work chart. It's a bit messy. It's just trying to fit it on the screen. And you can go ahead and double check. If you spot any errors, please email me, and I will get that out to the class. But that's how you can write a polynomial function of degree 4 when you're given limited information about the zeros. Granted, if any of these were changed instead of function, say they asked you to write an equation, you would follow the exact same process, but instead of having f of x as your answer, or f of x equals, it would be something of the lines of 0 equals. So with an equation, you're talking about roots, and you have 0 equals, whereas with a function, you're talking about a special relationship, and you're going to have f of x. Now let's summarize what we did in this. First, we recapped the fundamental theorem of algebra, and saw how we can rewrite polynomial functions using the x minus r1, x minus r2, etc. format. We saw a couple of conjugate theorems that tell us more information about roots and zeros when we're given certain information. If a plus bi is a root, then a minus bi is also a root, or a 0 if you're talking about functions. And then lastly, we saw how to write functions when we were given some information. Phil was writing or screaming at us to write, and we're kind of working backwards to what we normally do of finding the roots. So that's a summary of 5.7. In class, we'll look at Descartes' rule of signs and round off this topic. Thanks for watching this video lesson.